Professor Bialis here. In this video we are going to be covering section 4.4 where we expand a little bit and we get into three variable systems. Okay, now up until this point we were dealing with systems that had two equations with two variables. Here we're going to be dealing with three variables and then therefore three equations. Okay, we typically want to have the same amount of variables, same amount of equations to get a single precise answer. Otherwise we're going to have a multitude of answers if we don't have enough information in the form of enough equations. Okay, so the methods that we've dealt with in the past will also work here. We've dealt with graphing, substitution, elimination, or addition method. Okay, graphing, the problem with 3x3s is we're dealing with three-dimensional space now. That's going to be hard enough to graph, let alone accurately and find where all these things intersect as a single point. Okay, so while graphing it can be used, we're going to avoid that right now. Also, substitution. The problem with substitution is when we dealt with a two-variable system, we started with equations like this and then they turn into this. Okay, not a big deal. But when we have a three-variable system, we're going to start with equations like this, and if we go to substitute, the equation can end up like this. Okay, it'll be a solvable equation, but the longer the equation, the more opportunity we have for mistakes. So that's why we are going to go with the addition method to solve these things. Okay, you can use the others, but again, the addition method is the one that I like to present with this material. Okay, so we're going to jump right into some examples and see how this plays out. There's going to be a lot of algebra involved, a lot of good bookkeeping where we have to stay organized, but as always, I'm going to try to make this as routine as possible. Okay, we're still learning a skill here, so we want to get that skill down with just normal, regular routine. After that, if this pops up in some application later on, we'll have that routine to fall back on in order to solve this and find the information we need. Okay, so let's look at an example. Okay, so when we had our solutions in the past, we always had an ordered pair. Here we're going to have an ordered triple. Now the ordered triple that we're going to be looking for is always going to be x, y, then z. Okay. Also, another word of warning, since z is kind of a new variable that we're going to be working with here. If your 2's look like z's, be very careful. Either do that crossbar on the z here or change the way your 2's look. For years, I remember I would write my 2's like that. That's perfectly fine, but if you get sloppy, that 2 can look like a z. So once I started in algebra, that's when I started to make, my 2's with that little curly bar on the bottom. Okay, so just be aware of that, that can be an issue if we're not careful right off the bat. So let's look at how we can use the addition method to solve this thing. Okay, now when we were using the two variable systems, the addition method started us out with two variables and then we whittled it down to one and then we solved. Okay, here the same thing's going to happen, but we start with 3, whittle it down to 2, whittle it down to 1, and then we solve. Okay, so to start this is what I like to call a full system. There's an x, y, and z in every single one of the equations. So what I want to do with this is always pair them up. Now there's only 3 equations, so when you pair these up, there's going to be one equation you use twice. You can pair them up any way you like, but unless something is jumping out at you, what I like to do is the first 2 and then these bottom 2. So I'm using that middle equation twice. So I'm just going to rewrite those. And we have this. So again, first 2, last 2. Make that just kind of your mantra here. First 2, last 2. Now, I want to use the elimination method or the addition method to get rid of one of these variables. It doesn't matter which variable you get rid of. Is there any variable that eliminates on its own as it stands? These y's go away on their own. So let's utilize that. If it's ready to go, let's get rid of them. So I'm going to add down these columns to get 3x plus 2z equals 11. Okay? Now, what is important here? I eliminated the y because it was easy. But if I eliminate the y here, I have to eliminate the y here. Okay? It doesn't matter which variable you eliminate, but it has to be the same variable in each pair. I'll explain why in a minute. Okay, so if I want these y's to eliminate, I need to multiply this top equation by a negative 2. Remember, they have to be opposites, so that's why I have to throw a negative in there. So I end up with negative 2x minus 2y plus 2z equals positive 4. 3x plus 2y plus 2z equals 13. Okay? Now the y's cancel out by design. Negative 2 plus 3 is x, plus 4z equals 17. Okay? Now, the reason why I need to eliminate the same variable is I want the results to match. I have an xz equation here. I have an xz equation here. Now, why is that important? Because I went from 3 variables, and what did I say I needed to do? Whittle it down to 2. So what I'm going to do is now take these equations that I created and make a new 2-variable system. Like so. And now we're back to what we were doing in section 4.3 with solving a 2-variable system with addition. If you want to use substitution here, or I guess you could use graphing, but I would avoid graphing at this case, in this point. Okay, if you wanted to use substitution, you could. I would just stick with elimination though. Okay. Now, what I'm going to do is target these x's. So I'm going to multiply this equation by a negative 3. And what that gives me is a 3x plus 2z equals 11. Then a negative 3x minus 12z equals negative 51. The x's eliminate by design, and then I get negative 10z equals negative 40. Divide by negative 10, and z equals 4. Okay? Now, at this point we were moving forward. Now we're digging ourselves out. Okay? Now what I mean by that is now we're just going to use back substitution to find the remaining variables. Now here's the thing. We still have too many unknowns to go back here. That 2x2 we created, or the 2-variable system, I need you to finish that first. I found that z is 4. The next variable we should be after is the x. So I'm going to go with this one and get x plus 4 times 4 equals 17. X plus 16, and then x equals 1. Okay? So I've got my x, I got my z. I still need my y. Now the only place that we had a y were in these original 3 equations. Pick any one of these you want. Plug in the z and the x, and then we're left with a y to find. Okay, so let me go down here. I'm going to pick this middle one just because it seems simplest. So I have x plus y minus z is negative 2. So 1 plus y minus 4 is negative 2. Y minus 3, and then add a 3. And y equals 1. Okay? And then finally we can say x, y, z. And there's your answer. Okay? Now, let's recap, because this is a lot of work. However, it will be very routine after you do a bunch of these. You have a full system. There's no gaps. First two, last two. Eliminate the same variable in both. Create a new two-variable system. Solve that. Then use those two to plug in one of these to get the third variable. That seems like I'm oversimplifying it, but that's all we're doing. Okay? When I say eliminate a variable, the same variable here, there's a lot to that, but that's all we're doing. Okay? And we should be at a point now where if I say eliminate the y's, you know how to do that. Okay? And if you're not, that's okay, but we need to try and get there. We need to keep repeating that process so that when I say do this, boom, I know how to do that. Okay? Turn on your car. You don't have to think about that. Turn your turn signal on. You don't have to think about that. Okay, same thing here. We want to get the repetitions down so that the workings behind those steps become a little bit more automatic. Okay, let's look at a few more of these. So again, we are given a full system. Your first reaction, I want it to be, write the first two. And the last two. Okay? Now, I'm going to look to see if there's any variable that eliminates as is, okay? And if I look at this, I see that the x's right here will eliminate. So when I'm looking in both of them. So if the x's are going to eliminate right away, I can get 3y minus 2z equals 7. Okay? Now if the x is eliminated there because it was just the easy thing to do, what do I have to eliminate here? I also have to eliminate the x's. So in order to do that on this first set, I'm going to multiply this by a 2. So what I get is that first equation coming down, and then I distribute the 2. So negative 2x plus 2y minus 2z equals 12. Okay? And by design, that's gone. And then I have 6y minus 4z equals 15. Okay, what I just created are two new equations with two variables. So I created a two-variable system. So I'm going to go off to the side. And now my problem is this. Okay, so now I'm back to section 3. Now, in order to do this, I want one of those variables to go away. I'm going to target the y's just because they're in front. Okay, so to make these match, I'm going to make them both a 6. And I'm going to multiply that bottom one by a negative 2 to make them have opposite signs. So what I get here is that. Now, I was targeting the y's, and yes, in fact, they go away. But what else happens? The z's go away as well. I got nothing on this side. 15 minus 14, is 1. 0 equals 1, that's not true. So remember, when we saw that, what do we say? No solution. Okay? Sometimes you'll see in the book this empty set. Either way will work. Okay, either way that means the same thing. And that's it. There's nothing else to plug back in. There's nothing else to check. There's none of that. Once you hit that, no solution, move on. Okay? So let's then look at this one. This one's a little different. Okay? Now, this is no longer a full system. Okay? These gaps are in there just so everything still lines up. There's still the x's, y's, and z's. Okay? Now, remember, when we had a full system, we had to take first two, last two. You don't necessarily have to do that here. The reason we did that in the past was we had these 3 variable equations that we needed to whittle down to 2 variables. Notice they're all 2 variable equations, but they don't, no 2 of them have the same variables. We got xy, xz, and then yz. So what we're going to do is I'm going to pick one of these equations, and I'm going to hold on to it, okay? I'm going to pick this first one, and I'm going to bring it over so I can work with it later. Okay? I am then going to combine the other 2 in a way that will work with that equation. So I'm just picking one of these to hold on to. That's going to be kind of my model. I chose the first one because it's the first one. Okay? Now I'm going to use these other 2. Now, I need to eliminate one of these variables because in this mix, there's still 3 variables there. But I want to match this. So that means these z's need to eliminate. Okay? Now, in order to eliminate, I want them both to be a 6. So I'm going to multiply this one by a 3 and this one by a 2. Okay? Now, also notice they have the same sign. So I'm going to throw a negative on that, just so then they have opposite signs after I do the distribution. The other thing, remember back in the previous section, I said you could simply flip-flop these. That works here as well. Okay? So what we get is 18x minus 6z equals 12. Then negative 2y plus 6z equals negative 4. Okay, now watch what happens. The z's eliminate. That's what we wanted to happen. Now these have nothing to add with, so they just drop down. Because it's 18x plus nothing, well that's 18x. Nothing minus 2y is negative 2y. And then we get an 8 with those constants. So what we did again is we picked one, and once we push this to the side, we say, okay, we need to have another xy equation. So then we take the other 2, pull them together, and then we make a new xy equation. And this now is a 2-variable system we can solve. And if you look at it, this is actually really nice because those y's just eliminate on their own. So we have 21x equals 7. Divide by 21. And x is 1/3. Okay? Now, I said in the previous one, finish that 2 by 2, and by all means you can. Or, notice since there's gaps, I could plug the x in here and get the z, or the x in here and get the y, or the x in here and get the y that way. So you have a little bit more freedom after that, but to stay consistent, let's just stay here. Let's finish this. Okay, so I'm going to go with this top equation. 3x plus 2y equals negative 1. And I'm going to plug in the 1/3. So that's a 1 plus 2y is negative 1. Subtract the 1. And then divide by 2. And there's your y. We have x, we have y, we still need z. You need to go somewhere where there's a z. So I can go here, or I can go here, whichever one you prefer. The fraction's going to go away pretty quickly, but I still have to work with a fraction if I use this. I'm going to go with this one. Y is negative 1. I add the 1. And then divide by negative 3. And there's your z. So what I have is x, y, z. And there you go. Okay? It's just kind of a coincidence that we had negative 1, negative 1. They could be all the same number. They could be all different numbers. They could have 2 as the same. That just kind of happened to work out that way. Okay? So this is how you would approach a system that is not a full system, as I call it. If it's full, take bottom two, or top two, bottom two. Okay? Break it down into a 2 variable system and solve. Here, I'm going to keep one of the equations, then use the other 2 to create a new one that matches it. Okay? So same basic concept, but this requires a little less work because we're kind of halfway there when we have all those gaps. So let's look at a couple more. Now, again, we don't have a full system here, so we are going to pick one of the equations and push it off to the side to be used in the second phase. Okay? However, which of these equations do we not want to hold on to? We definitely don't want to hold on to this first one because there's 3 variables in there. We're looking for an equation that has 2 variables. So we could pick either this one or this one. I'm going to stick with this one simply because it's a nice, clean x plus y. So I'm going to hold this off to the side. Okay? I literally just take this, push it over. I then am going to use the other 2 to combine them into a new equation that will work with that. So I'm going to focus now on these. Okay, now be careful. If you look at this, then you might think, well, I'm going to go after these x's because that's pretty much ready to go. I can eliminate those very easily. But remember, my result here has to work with this. So it's no longer what's the easiest way to do it. I need to look for something specific. I need to eliminate the z's. Okay? So what I do to eliminate those z's is multiply this bottom one by a 3 and then a negative 3, okay? Because I need them to have opposite signs. So what I get is 2x plus 5y minus 3z equals 30. Then negative 6x plus 3z equals 0. That eliminates. 2 minus 6 is negative 4x. 5 and nothing is 5y. and then 30 plus 0 is 30. And now I have a new xy equation that I can pull together with this. And now I solve this. Okay? Now, you can eliminate either one of those that you like. I'm going to go after the x's simply because they already have opposite signs. So I'm going to multiply this top equation by a 4. And we're here. The x's go away as we planned. And then we've got 9y equals negative 12 plus 30 is 18. I can divide by 9. And there's my y. Okay, let's finish that system. I'm going to find the x next. So I've got x plus y equals negative 3, or x plus 2 is negative 3. Subtract the 2, and x is negative 5. Okay, after that I still need to find the z. Now I have to go someplace where there is a z. So I can go here and solve for the z, or I can go up here and solve for the z. They will give you the same result. But in this case, since we have an option, pick the easier option. I'm going to go with this. So I'm going to have 2x minus z equals 0. So 2 times negative 5 minus z equals 0. That's negative 10 minus z equals 0. Now, normally we would add the 10 but then divide by the negative 1. Here's an alternative. I could just add the z. Doesn't have to be on the left. And then we get negative 10. So what we get is x, y, z. And there's your answer. Okay? Let's do one more. Okay. So, in this case, we're back to a full system. So when we have a full system, like I said, I would just automatically first two, last two. Okay, if you want to be a little bit more creative with how you pair them up, you can, but I wouldn't force that. Just first two, last two will work. Okay, so on this one, we want to eliminate a variable, or the same variable in both sets. So does any variable eliminate as is? In this case, nothing. So we have to do some work regardless. Now, I'm going to pick a variable, and I'm going to stick with it. Okay, so I'm going to, let's say, eliminate these z's. Okay, and I'm just picking z. Okay, there's no rhyme or reason necessarily, I'm just picking z. I want to target these z's. So, in order to get those to eliminate, I am going to multiply this top one by a 2. They already have opposite signs, so I just need to make that top number an 8. So what I'm going to get is that, and then I bring this second equation down. Okay, so we did a good job. That eliminates. but so does that, so does that, and so does that. So what we're left with is nothing here, nothing there. Now, when we saw that, what did we always say? That's when we had that infinitely many solutions, okay? Or in this case, we're going to do kind of the same thing as we did with the two variable equations, or two variable systems. But here we're going to say I have x, y, z ordered triples such that it has to work for this equation. Now, I'm going to pick any one of these I want. I'm going to go with this top one just because the numbers are smallest. So I'm going to go with x minus 3y plus 4z equals 2. And there we go. Okay. Now, again, that shows that you have an infinite number of solutions, but this is the descriptor of how we find those solutions. Okay. Now, for our purposes here, that's all we have to show and all we have to do. Okay. If you wanted to kind of take this a step further to verify that this is true, what we should do is eliminate these, and you'll find that you'll get a 0 equals 0 there as well. Just real quick, let's show that. Let's say I multiply this by a 2 to clear those fractions. And I get x minus 3y plus 4z equals 2. But then I multiply this by a 2 again, and I copy that first equation. Oops. And I get 2x minus 6y plus 8z equals 4. And as you can see, you again get a 0 equals 0. So if you get a 0 equals 0 here, you should get the same thing here. So if you want to do both just to verify, that's not a bad idea. Okay, I will give you a word of warning though. When you deal with this in like a college algebra setting, there's a little bit more that can happen when we have an infinite number of solutions. Okay, here they're keeping it very, very simple, straightforward, the simplest situation you can run into. Okay, so there's a little bit more to it, but you won't see that here. You're going to see that in the future. Okay, just to give you a kind of a heads up on that. Okay, so that is 3 variable systems. You have a full system, you have a not full system. The not full system requires a little bit more finesse because you have to pick one of those variables and so on, but it requires a little less work. Okay, so try to make this as routine as possible. If it's a full system, first 2, last 2, and then eliminate a variable. If it's not a full system, pick one and then make the other, combine the other 2 to match that one you picked. That's pretty much all there is to it. Okay, so be careful with your work. Try to be as neat and as organized as possible, and you'll do great. As always, let me know if you have any questions. Keep working hard, and I'll see you next time.